Chapter 26 The Space-Time Continuum of the Special Theory of Relativity considered as a Euclidean continuum. We are now in a position to formulate more exactly the idea of Minkowski, which was only vaguely indicated in section 17. In accordance with the special theory of relativity, certain coordinate systems are given preference for the description of the four-dimensional space-time continuum. We call these Galilean coordinate systems. For these systems, the four coordinates x, y, z, t, which determine an event, or, in other words, a point of the four-dimensional continuum, are defined physically in a simple manner, as set forth in detail in the first part of this book. For the transition from one Galilean system to another, which is moving uniformly with reference to the first, the equations of the Lorentz transformation are valid. These last form the basis for the derivation of deductions from the special theory of relativity, and, in themselves, they are nothing more than the expression of the universal validity of the law of transmission of light for all Galilean systems of reference. Minkowski found that the Lorentz transformations satisfied the following simple conditions. Let us consider two neighboring events, the relative position of which in the four-dimensional continuum is given with respect to a Galilean reference body K by the space coordinate differences dx, dy, dz, and the time difference dt. With reference to a second Galilean system, we shall suppose that the corresponding differences for these two events are dx prime, dy prime, dz prime, and dt prime. Then, these magnitudes always fulfill the condition dx squared plus dy squared plus dz squared minus c squared dt squared equals dx prime squared plus dy prime squared plus dz prime squared minus c squared dt prime squared. The validity of the Lorentz transformation follows from this condition. We can express this as follows. The magnitude ds squared equals dx squared plus dy squared plus dz squared minus c squared dt squared, which belongs to two adjacent points of the four-dimensional space-time continuum, has the same value for all selected Galilean reference bodies. If we replace x, y, z and square root of minus 1 multiplied by ct with x1, x2, x3, x4, we also obtain the result that ds squared equals dx1 squared plus dx2 squared plus dx3 squared plus dx4 squared is independent of the choice of the body of reference. We call the magnitude ds the distance apart of the two events or four-dimensional points. Thus, if we choose as time variable the imaginary variable square root of minus 1 multiplied by ct instead of the real quantity t, we can regard the space-time continuum in accordance with the special theory of relativity as a Euclidean four-dimensional continuum, a result which follows from the considerations of the preceding section.